Tu educación es una oportunidad para crecer, para brillar y superarte ante la adversidad. En la UISEK somos tu segundo hogar y mantenemos la excelencia académica como la bandera que nos caracteriza, con un ambiente cálido y humano pensando en ti. Permanezcamos unidos y seamos fuertes en el camino. Cuenta con nosotros para mejorar tu futuro. Universidad Internacional SEC, personalización en serio.
Bienvenidas y bienvenidos al evento Uso del Modelado de Información de Construcción para facilitar la aplicación de sistemas robóticos en la construcción, organizado por la Universidad Internacional SEC. Welcome to the webinar Use of Building Information Modeling to Facilitate the Application of Robotic System in Construction, organized by the SEC International University. I want to give the floor to Néstor Llorca, Dean of Architecture and Civil Engineering. Quiero darle la palabra a nuestro decano, Néstor Llorca, decano de la Facultad de Arquitectura e Ingeniería Civil. Bienvenido, Néstor.
Sí, buenos días. Muchas gracias por dejarme participar un momento. Esta es una actividad organizada por la Facultad de Ingeniería de la universidad, pero yo voy a participar en un momento justo porque el tema que nos convoca ahora es transversal a las dos facultades. Quiero agradecer a Camila por su participación y a las personas de la Facultad de Ingenierías por dejarme participar, y solamente es por comentarles una cosa. Este tema que va a tratar ahora Camila, que es parte de una migración a un nuevo paradigma sobre el uso generalizado de la construcción a través del BIM, ahora tiene un programa de maestría en el Ecuador, el primer programa de maestría de BIM, que es hecho por la Facultad de Arquitectura de la Universidad SEC, que tendrá su primera cohorte ahora en octubre. Entonces era solamente para comentarles esto, para recordarles que tenemos ahora una maestría que tiene una relación directa con lo que Camila nos va a hablar posteriormente, y que ya es una oferta para las personas que están en el Ecuador. Entonces nada más de eso, agradecerles nuevamente el espacio y espero que disfruten de la conferencia. Les dejo ahora con Gustavo Moreno, que es el coordinador de la carrera de mecatrónica y que va a hablarles ahora de la presentación de Camila. Gracias.
Muchas gracias a nuestro decano Néstor Llorca, decano de la Facultad de Arquitectura e Ingeniería Civil. We have the presence of Gustavo Moreno, professor at the Faculty of Engineering and Applied Sciences, who will give us the words of welcome. Bienvenido, Gustavo Moreno, docente de la Facultad de Ingeniería y Ciencias Aplicadas de la Universidad Internacional SEC, quien nos dará las palabras de bienvenida a este webinar.
Muchas gracias, Karen. Buenos días con todos nuestros asistentes. De nuestra parte, en la Facultad de Ingeniería y Ciencias Aplicadas, queremos agradecer mucho a nuestra invitada, Camila Follini, del Italian Research Innovation Engineering Center, con su ponencia Use of Building Information Modeling to Facilitate the Application of Robotic Systems in Construction. No nos cabe más que recalcar la importancia de estos webinars internacionales que nos invitan a visualizar las tecnologías de punta y el estado del arte en el uso de información y la robótica, siendo estos conocimientos esenciales para el apoyo a nuestras carreras de pregrado, como lo son mecatrónica e ingeniería industrial. Muchas gracias y bienvenidos.
Muchas gracias, Gustavo. Queremos presentar y darle la más cordial bienvenida a nuestra ponente. We want to give the warmest welcome to our speaker. Camila Follini es investigadora del equipo de Ingeniería de Procesos en Construcción. Obtuvo una maestría en Arquitectura en la Universidad Politécnica de Milán y una maestría interdisciplinaria en Construcción Avanzada y Tecnología de Edificación en la Universidad Técnica de Múnich. Su tesis de maestría fue desarrollada bajo la supervisión conjunta del Departamento de Arquitectura e Ingeniería Mecánica en colaboración con Kewaso, una startup que desarrolla un sistema robótico para automatizar la logística y el montaje de andamios. Durante sus estudios, trabajó como asistente de investigación en la Cátedra de Realización de Edificios y Robótica de la TUM. Actualmente es estudiante de doctorado industrial, donde está profundizando su investigación sobre cómo cerrar la brecha entre la robótica y el sitio de construcción. Camila Follini is a researcher in the Process Engineering and Construction team. She received a master's degree in architecture at the Polytechnical University of Milan and an interdisciplinary master's degree in advanced construction and building technology at the Technical University of Munich. Her master thesis was developed under a joint supervision of the Departments of Architecture and Mechanical Engineering in collaboration with Kewasu, a startup developing a robotic system to automate scaffolding, logistics, and assembly. During her studies, she worked as research assistant, the chair of building realization and robotic of the TUM. She is currently an industrial PhD student. Thank you very much, Camila, for being here with us.
So thank you, Karen, for the introduction. I will now share my my presentation with you. Okay, great. So thank you a lot for having me here. So as you mentioned, I am a researcher at the Fraunhofer Italia Institute and a PhD student at the University of Bolzano. And today I'm going to present you one of our ongoing research, which investigates the use of building information modeling, BIM, to facilitate the application of robotic systems in construction. As many of you probably already know, there is a productivity gap between the building industry and the other industries such as manufacturing. That is because, among the other reasons, is that the use of advanced technologies such as robotics, although is constantly increasing in the manufacturing industry, it cannot be used in construction due to mainly to the big differences between the construction site and factories that concern, among others, the complexity of the product, which is the building that always changes because for the project, the typology of the building, the materials, shapes, geographic location, and so on. Then for the unstructured work environment, that is the construction site that is usually very dirty, and it has no clear layout, and is also constant under constant change. Then you have in a building project, you usually have a large number of stakeholders and a very complex supply chain that make the factors that make the innovation difficult. Moreover, usually construction stakeholders are kind of skeptical towards new technologies and prefer to stick to conventional practices. And finally, if you consider the integration of a robotic system in construction processes, you will need to consider that it would have to coexist or share its workspace with humans. So that means that it would need to have a very strong safety standards. However, advanced technologies and robotics could really greatly help the construction industry, and that is not only because construction is almost always at the top industries for accidents and injuries, but also because it is one of the most riskiest industries for musculoskeletal disorders on the long run. And that means that workers need to do all the movements that you see in this graph for construction tasks that put a strain on the body, so that they usually retire early and have chronic pain even after retirement. So for this reason, construction is also losing attraction towards younger generations, and especially in most developed countries, it is experiencing a shortage of workers. So that means that automation in this case could greatly help to relieve some of the strain that workers are going under. So, however, at the same time, in the latest years, we could see that there are some trends that could bridge these two words that are seemingly so apart from each other, which is the construction site and robotics. On the one hand, industrial robots or robotic manufacturers are striving to achieve more flexibility with their solutions, and that is to respond to a need of the market that asks for more customization of goods. So that means that the robotic solution are not anymore mass producing goods, but they need to adjust to different products and need to do so fast, so that there is a new trend, which is collaborative robotics or cobotics, that is that are robots that are going outside of their cages and are working alongside humans to produce together manufacturing goods. On the other hand, from the construction side, we see that there is we're trying to achieve more structuring of the construction processes, and this is possible thanks to the increase of digitization in general in the industry, and a very large part of this is thanks to the new methodology of the building information modeling. BIM can be described as this new methodology based on digitization that is aimed at collecting and organizing increase a very large amount of data on the building that can be used in its whole life cycle. So as you see here, if with CAD we had already a first revolution, so we had the graphic image on a computer in 2D and 3D representing the geometry of the building and its components. With the BIM, we have a larger amount of data, also object-based, so always linked to a building object that could be, for example, a wall, a window, a door. They contain not only the geometric information, but also different kinds of information that compose these so-called dimensions. So for example, if I have information on scheduling on site, on the construction date, then I would have 4D information. If I have information on cost, 5D, BIM, and so on. And finally, all these data can be exported in this open format, which is the Industry Foundation Classes, IFC, that structures all this information meaningfully with the same structure. So this brings indeed synergies with robotics because the BIM strives to reduce communication errors between the different stakeholders of the construction industry, and that is by bringing together information from all the actors at the beginning on the process, so in some cases even as early as at the design stage. And then it provides, as I said before, detailed information on all the objects contained inside of the building. And this information is structured always in the same way, so it could be easily retrieved. And then the data is organized throughout the building life cycle. So that means that from the design stage, I could use this information not only for construction, but also for operation and maintenance of the building and so on up until the demolition and the end of the life of the building. So all of this put together with the fact that BIM is constantly spreading in the construction industry and will soon become a standard, all of this concur to say that the BIM, and especially Open BIM, will play a fundamental role for the application of robotics in construction. So the idea behind our project was to bridge Open BIM with another key player of open source, but in the robotics side, which is the Robot Operating System, ROS. So ROS is supported by the Open Source Robotic Foundation, and it is used often in research for rapid prototyping. A strong advantage of this operating system is that it has a very large open source community of developers that share tutorials and projects, and this leads to a global teamwork of researchers that work together to solve complex goals. And another advantage is that it has a strong modularity, so that it enables the development of modules that can be integrated easily in different projects, so that a solution studied by one researcher could be easily exploited by another researcher for another project. So in our research, we had the use case of developing this robotic assistant for on-site logistics that would follow an operator on the construction site while carrying heavy loads. So a system like this would have obvious advantages, such as the reduction of the transportation times of materials and equipment that is a task that brings no added value to the construction process overall, but needs to be done. Then, of course, the reduction of fatigue for construction workers, so that it would bring an improvement of the long-term health of them. And then an increase of productivity, since the workers can focus on more important works that require human intelligence and more quality. However, it also has stronger challenges. It's also a challenge because the robot would need to navigate in the unstructured environment of the construction site, and also the environment constantly changes over time. And it would need to share its workplace with workers that usually have a low level of experience with robotic systems. So to summarize our research objectives, we made this diagram. As you can see on the leftmost side, we have the OpenBIM file, the IFC, which is used as a database to create a ground knowledge for the robot about the world. This knowledge is based on is an a priori knowledge of the BIM objects that are in particular studied by geometry, by information on their scheduling on the construction site, and then on other kind of semantic information that is retrieved by reading the IFC parameters and, for example, IFC types. Then on the rightmost side, we have the real world, in which the robotic system is supposed to interact by supporting and collaborating with workers during construction and maintenance. And in the middle, we, of course, have this robotic system that is equipped with its own sensors to have an interface with the world. So to, for example, have dynamic obstacle detection, because we suppose that the BIM does not completely overlap with the real world, of course, because of the unstructured nature of the construction site. And it needs to identify workers and to have safety measure when it encounters them. And however, having data from both the BIM and the real world, it could also compare the two, so that it could see if there are many big discrepancies, or just to have information on the construction progress in general. So we made two prototypes in the first development phase. As you see in this picture, we worked indoors. For the robotic platform, we use this outdoor UV, which is the Husky A200. It is equipped with two 2D LiDAR sensors to check for dynamic obstacle detection. And then we had a fixed tracking system to track in real time the user and the robotic platform thanks to these spherical markers. In the second development phase, though, we wanted to overcome the most obvious shortcoming of the first system, which is the fact that it could work only indoor with this fixed tracking system. So in the second development phase, we used only sensors that could be mounted on the platform itself. And that is, we kept one of the LiDAR sensor and we used this RGBD camera mounted on the platform. About the transfer of knowledge from the BIM, we decided to focus on the open BIM file, so the IFC format. And we use this model, which is the model of our facilities in Bolzano, where the original lab with the fixed tracking system is located. And then we parse the IFC file to retrieve all the objects of the model. And that is, so the object together with its properties and geometry. So that having this information, we would then create a map that could be read by the robotic system. In this case, we wanted to create this grid map, which is composed of two kinds of pixels. So the black pixel represents an obstacle, and the white pixel represents a free space. And in the end, so an outcome which is very similar to a regular floor map, however, with some differences, because we create these maps so that they are time dependent. So based on the 4D BIM information, and for example, other differences are that holes in the ground, such as the elevator shaft, for instance, are obstacles as well. So to give you an idea of how elements are retrieved, the semantical properties of the object are retrieved from the IFC file, we give two examples. The first is about a non-physical entity, which is an IFC space. They are used to name the rooms in the IFC. So in our algorithm, they're used to give semantic information to the robotic system, so which room is which, and other information they could give is also spaces in which the system should not go, is not allowed to go. While for physical entities, the example of properties is more straightforward. So for example, for entities that should be mounted, we could have properties such as the installation date, installation state, whether it is installed or not, and so on. So they are easier to imagine. So about the time-dependent building maps, we start from this IFC file, and after retrieving all the objects, we go through this filtering, which is first geometric, so that we keep only the elements that have a risk of colliding with the robotic platform, just because due to their shapes, or we have the and the second filtering is about the for the beams, so the construction date, so that we keep only the elements that are meant to be built at the day in which the platform is used. So after this filtering, we keep in the code only the remaining object, and of these we create this map, such as we would create a floor plan. So by creating a 2D plane and intersecting it with the 3D object, and plotting with a camera on the top, in a top view, to create this picture. And to send it to us, we need to create an additional file, which is a YAML file that gives more information about the this image, such as the origin and the scale, for example. And then we use this, we send this YAML and picture to the map server, which is an existing node in ROS. And that sends this information to the navigation stack, to the global map, so that it is delivered to the robotic system this way. And this is the result in ROS. This is from the first implementation. As you can see on the right, the beam map is overlapped to the map that is created by the LiDAR sensors. And the robot in the lab was avoiding this obstacle in the middle of the room, which was strictly virtual. For the second implementation step, we wanted to cover a larger area of our facilities. So you can see this is the floor in which this lab is located. We wanted to expand, but to keep the same elements. So we have this temporary obstacle, so that is here for a shorter amount of time, but it's not part of the building itself. So we wanted to demonstrate that the a priori knowledge from the BIM could help the platform navigate. So the lab is the position of the laboratory is given through these IFC spaces, through the knowledge of the room. And this temporary obstacle is shown in the map given by the BIM, but not on the regular map of the building. So in this case, an example of navigation that could be enhanced by the a priori knowledge of the BIM is this. If I have this goal in the map and I start from this point, for example, the regular navigation stack would calculate the shortest path that is passing through this corridor, without, of course, knowing that there is an obstacle in this point. So the robot would reach this point and then start to replan its route and start to go to the lowermost corridor. However, with the a priori knowledge of the BIM, the platform would calculate from the beginning that since there is an obstacle here, the shortest path is the one going in this direction, so that it will save lots of time. And that is the experiment we made. So we have this fixed goal point, and then we randomized the starting point of the platform, and we repeated this for 5,500 times per map, so for a total of 9,000 times, so with and without BIM. And as you can see, on a general basis, the system performed better with the a priori knowledge of the BIM. There were some cases in which the system would perform better without the BIM, and there were when the path was not intersecting the temporary obstacle. However, when the path was intersecting this obstacle, the overall time was the BIM integration could save about from 20 to 60 seconds of execution time, depending on where the starting point was. So to go back to the example here, if the starting point was in the upper part of the map, then save less time, because at some point the leader could sense that the obstacle in a shorter time, so that it could replan its route beforehand. However, the BIM knowledge could save a lot of time if the system was starting at in the lower part of the map. So here, then it will need to again do this replanning, reach some point in the upper part of the map, and then replanning its route. And finally, we integrated a way to, again, collaboratively say some information from the robot to the BIM. In this case, in our use case, we consider that an operator would input that the installation was performed of an element, and in our interface we implemented a way to simply rewrite the nominal value of the IOC parameters, just so to have a very quick return of information to the BIM file. So our project is still ongoing. Till now, what we achieve is that we interfaced BIM with the robot operating system, so that we can retrieve from the BIM these metric grid maps and metadata for navigation that is more semantic. We also implemented this follow me feature, so that you could follow the operator in the laboratory and outdoors, and the automated obstacle avoidance for any obstacle that is not foreseen in the BIM file. So for the next steps, what we plan to do is to expand on the return of information to the BIM that for now is very basic, but we wish also to implement a way to get information from the point cloud that is retrieved by the LiDAR sensor, and to have a comparison with the IFC model. Then the application to the system not only in construction and maintenance, but also during the operational phase of the building, so for facility management. And finally, we plan to have some testing on a real construction site. So thank you for your attention, and by all means, if you have questions, I would like to answer them. Thank you.
Thank you very much, Camila. Yes, we have some questions through the YouTube channel. The first one is, how could we combine robotic system in tissue engineering? Would it apply to the construction of scaffolds?
So for the construction of scaffold, sorry, didn't get the first part of the question very well.
Yes,
Can
sure.
you repeat?
How could we combine robotic system in tissue engineering? It applied to the construction of scaffolds? So
BIM, I think that BIM is a very powerful tool also for the planning of the construction site. So also all this temporary structure that are, for example, scaffolding, but also other are in the larger projects. Of course, they are pre-planned before the establishment of the construction site, and there are also ways to make a simulation of the construction progress. So just by knowing the BIM and the information from it, we would have a lot of information for that can be read by a robotic system. Means that the structure of the IFC is always the same, and it could greatly help to have this interface between this BIM, for the BIM in this case, if we mention scaffolding, so a BIM with also temporary works and a robotic system. So I think it could have potential also in this direction.
Great. Thank you very much, Camila. The second question is, what safety measures should a human worker take for a correct application of building information modeling, and how profitable it is to train a worker in this area?
So for safety precaution in the building information modeling, it is for sure useful to train somebody to the use of a robotic system if we consider that we integrate one in a construction site. So if we make the hypothesis that we have a robotic system on site, then of course not only the robotic system will need to be adjusted for high safety, but also the workers should be trained to use it. The collaborative robotics already has many safety standards in this direction, such as, for example, the not only on the software, also on the hardware. The hardware should be round. There should be no edges or parts that could harm human, and so on. So this is the kind of safety measures that not only, of course, also on the software side, it should be 100% sure of not harming the workers. And on the BIM side, it really depends on the use of the robotic system, which task it is performing, or how it is employed on site. So it is difficult to say, but I know for sure that BIM is used for safety plans for the construction site, that those that are already used. So I think they could be embedded inside of the BIM for sure.
Great. Thank you very much, Camila. We have another question. What are the disadvantages of the implementation of this technology in the industry?
So the disadvantages of robotics are mainly in a construction site are mainly that there is they still lack the flexibility, of course, of a human mind. So one could say that now we are research is striving to increase the intelligence of the systems, but of course they are still at a very early stage, and they still need major work, especially in structured environments such as the one of the construction sites. For this reason, the first disadvantage would be that right now, at this moment, they would have great costs that would discourage construction companies to acquire one of these systems. However, it is expected in the next years, so when the intelligence will increase, the hardware costs will decrease, and so on, it is expected that robotic system could also tackle these industries where right now they seem too futuristic for, so construction and agriculture and so on. So it is meaningful to start researching them now, because it is indeed where we are headed anyway.
Great. We have so many questions. So let's say only, I think, 2 questions more. A construction site is a place that is constantly changing. You can put a ladder, scaffolding materials. Every time you have a change, should you do a new modeling of the site?
No, like I understand the question because I showed that we had this ladder, you know, these cones. The idea behind that is that we use these models that are usually done for larger construction sites. So the ones that actually make this 4D simulations in BIM, so that we have a major idea of this temporary structure. So if in my drawings we had just this ladder, like usually you have these models that have, as said before, scaffolding or other like machinery, larger elements that are more important to know where they are or what are, for example, their reach, if I consider a construction machine. So if I have this macro information, let's say, it could be very meaningful. And then for the obstacles that are more temporary, such as ladders or other smaller obstacles, then we have the obstacle avoidance inside of the robotic software. So the smaller obstacles are avoided that way. And then we could use the BIM, just a single BIM model comprising all of the 4D information for the major temporary structures and machinery or machinery locations, or I don't know, logistic points where the material is stored, points where the material is loaded, unloaded, this kind of information, which is more meaningful to have in the BIM model.
Perfect. And the last question we have is how long it will take to implement this technology in the Latin American countries?
I think that like Latin American countries would not be too different from our market here in Italy. So I would say that this kind of technology will probably be adopted sooner in countries like, for example, the United States or China, where they are more prone to innovation, and they are adopting, disrupting innovation more easily. Here in Italy, for example, construction is also very conservative, and it has very strong safety regulations. So it's not that easy to not even test this kind of solutions on a real construction site, because you always have to assure that workers are safe, that there is no risk of anything happening on the construction site. So I think that also probably Latin America will be like we are, so that we will have this kind of technology could be adopted probably later. But I think that there is also the possibility of having some sooner than others. So there is research going, for example, towards a platform like the one I showed, but it is navigating just to retrieve the construction progress. So it's going autonomously, and when there are no people on the construction site, and this kind of technologies will for sure be much faster to adopt than other that are collaborating with workers or manipulating the environment, for example.
Great. Thank you very much, Camila. Thank you for the webinar, Use of Building Information Modeling to Facilitate the Application of Robotic Systems in Construction. It was a pleasure to have you here with UISEK International University. Have a nice day, and thank you very much.
Thank you. You too.
En los momentos de crisis, tu educación es una oportunidad para crecer, para brillar y superarte ante la adversidad. En la UISEK somos tu segundo hogar y mantenemos la excelencia académica como la bandera que nos caracteriza, con un ambiente cálido y humano pensando en ti. Permanezcamos unidos y seamos fuertes en el camino. Cuenta con nosotros para mejorar tu futuro. Universidad Internacional SEC, personalización en serio.